All right. So this section is called polar coordinates. All right. And so we're going to start off with what we know, which is very similar to what we just saw in the last unit, which is when we have an XY plane or a Cartesian plane, we can graph points by knowing the X and the Y values. So for example, this green point up here means that I went over to the right 2 and I went up 3. Whereas this red point over here to the left, I went to the left 3 and I went up 1. And that we know how to do, okay? And so what we briefly talked about earlier, but not very much, was that we have this new way of writing coordinates when we have these circle grid looking things, okay? So this is called a polar coordinate plane. And the points are written in the form r, comma, theta, right? Like we talked about earlier. Now, the way that we find these is we go to the angle first, and then we count out however many circles the first number sets. So for example, for this coordinate right here, I go to pi over 6, which is right here, and then from the center, I count out 1, 2 circles, and so that's where my point is, okay? I could do the same thing with those other points there. Those are just example points to show you that the r comes first and the theta comes second, but usually we find the angle first and then we count out that distance, okay? So, I'm graphing polar coordinates. Let's go back to some basics, okay? So we're gonna do 2 examples. We're gonna graph a few different points and see if we can get the hang of this. So in point A, let's do that in blue. So I'm going to go to pi over 4, and then from the center, I'm going to count out 3 circles. So 1, 2, 3. So 3 comma pi over 4 should be right there. Does that make sense to folks?
Yes.
Yes, okay. So for coordinate B, I'm going to go to pi over 2, but this time I'm only going to count out 2 circles. And so that's where point B would be. And point C is 4 comma 4 pi over 3. So I'm going to go to 4 pi over 3, and I'm going to count out 4 circles. And so I end up with this as point C. All right, let's keep going. So on a different graph, let's graph the points D, E, and F. I'll give you a moment to kind of visualize where the points might be, and then we'll graph those together. All right, so 9 pi over 4, where is that?
In pi over 4?
Yeah, it's the same place as pi over 4, right? We just keep counting until we get to 9 pi over 4. And so 9 pi over 4 is equivalent to pi over 4. And then I'm going to go out 3. So point D is actually the same as point A from the previous graph, right? They're in the same place. So point A and point D are the same point. That's one of the interesting things about polar coordinates is that a coordinate can have more than one name, okay? All right, let's try point E. I'm going to pi over 2, yeah? Now, how do I get to negative 2?
Would you go down 2?
Yeah, you do. That instinct is real good. So I go to pi over 2, but instead of counting up 2 like I did for B, I go down 2, and this will give me point E. Okay, so that negative, if the distance is negative, it just means go in the opposite direction of that line. Literally turn around and go 180 degrees in the opposite direction. Okay. All right, we've got one last point here, F. So we're going to go to negative 2 pi over 3 and then go out 4 circles. So where is negative 2 pi over 3?
Four pi over 3.
Yeah, we're just counting backwards. And so that's going to be at 4 pi over 3. And we're going to go in that direction 4 circles. So point F is actually also the same as point C. Okay. So when we're talking about polar coordinates, there's more than one name for every single point. Okay, you can come up with an infinite number of names for every single point. Sometimes it's more useful to use one version rather than the other. And so that's why it's important to know that we can just choose different names for the same point. Okay.
Is there any way you could show how you got 4 pi over 3?
Yeah, because I start here and I count negative 2 pi over 3. So this is negative 1 pi over 3. And negative 2 pi over 3 is right here.
Okay, thank you.
Okay, so you're just counting in the opposite direction. All right, so it's important to know how to convert between polar and rectangular. We kind of talked about that earlier with complex numbers, but it's different if we're looking at real numbers, okay? So now we're looking at real numbers, the regular XY numbers, and so here are some equations that help us convert between rectangular and polar coordinates, okay? So if you have r comma theta, and you want to convert it into xy, you use this one. So you have r comma theta, and you want x comma y. Okay? So that's going to be like example 3. So let's try it out. I have my r is 3, and my r is 3, and my theta is pi over 4. So if I want to find the x coordinate, that's going to be 3 cosine pi over 4, which is 3 times root 2 over 2, which is 3 root 2 over 2. And then we do the same thing for the y. Y equals 3 sine pi over 4, which is 3 times root 2 over 2, which is 3 root 2 over 2. And so together we get our rectangular coordinate. And so we just write the x and the y. And there we have it. Okay. So if we plot 3 comma pi over 4 on a polar coordinate, and then we graph 3 root 2 over 2 comma 3 root 2 over 2 on a rectangular coordinate, and we laid the graphs on top of each other, they would be the same point. All right, the other equation set that we have here is what we use when we have x, y, and we want r theta. Okay, and this should be very familiar from the last section because it's essentially the same thing. Okay, so let's take our rectangular coordinates. I have an x of -1 and a y of 3. So if I want to find my r comma theta, I need r equals, and I could actually write this as square root of x squared plus y squared, that distance formula that we talked about at the very beginning of 12.1. 8.3, okay? And so when we plug this in, we're going to end up with 1 plus 3, or square root of 4 is 2. Now, to find our theta, we know that theta, and someone mentioned this earlier, is the inverse tangent of the y over the x, or inverse tangent of root 3 over negative 1, okay? And what angle is that? And it might be helpful to know what quadrant your point is in.
Would it be in quadrant 2 and 5 pi over 6?
It is quadrant 2, yeah, because negative 1 and then root 3 is in quadrant 2. But we need the y value to be bigger than the x value. That's not 5 pi over 6. That's actually at 2 pi over 3, okay? So once we have our r and our theta, we can go ahead and write one set of polar coordinates. So we can write it as 2, comma, 2 pi over 3. And if I wanted to sketch that, I know that would be 2 pi over 3 and then out 2 circles, so like somewhere over here. What would be another name for this same point?
-2, 4 pi over 3.
Where's 4 pi over 3?
In quadrant 3.
It's in quadrant 3. So if I want the negative, that's going to end up in quadrant 1 somewhere. So I like the thinking, but let's pick a different angle.
Okay.
What angle, if we have an r of -2, will still get us to 2 pi over 3?
Five pi over 3?
Yeah, it's the one directly across from it. So if you have your unit circle, go directly across, and that'll tell you which angle to choose, okay? All right, let's get one more name for this polar coordinate.
Would it be 2 -4 pi over 3?
-4 pi over 3. All right, let's count. Well, this would be -3 pi over 3. And yeah, this would get me to -4 pi over 3. So I like the angle, -4 pi over 3. And I'm sorry, what did you say for the r?
Just 2.
2. Good, very good. Okay. So different ways of naming the same point, useful in different formats, but we're not at that stage where we're ready to make that decision yet. In this course, we're really just focused on like, how can we know that there are different names for them, okay? All right, so that's the converting of coordinates. But now let's talk about converting between polar and rectangular equations, okay? So we're gonna use the same equations from above, but now we're plugging them into equations, okay? Because where we're going in this course is trying to figure out, like, just like we know y equals mx plus b is a line, like how do we know what shape these different polar equations are? Because they're not necessarily as straightforward as knowing y equals mx plus b or y equals x squared, okay? So let's take a look at this polar or this rectangular equation. So if I have xy and I want to find the polar, okay? let's go back up for a moment and take a look at which equations we should use. We have xy, we want polar. That means we're gonna grab these equations to help us out. Okay, r squared equals x squared plus y squared, and tan theta equals y over x, all right? And I'm also gonna grab these ones to write them down below, just so that we have a list of all of those, okay? So our equations are r equals, whoops, r squared equals x squared plus y squared. Tangent theta equals y over x. And then we had x equals r cosine theta, and y equals r sine theta. Okay. So what might be a good substitution to make to start to get this equation with r and theta instead of x and y?
Factor?
I wouldn't factor, no. It's not factorable anyway. X squared plus y squared doesn't factor.
Yeah, I just realized that. That's
Yeah.
a yeah.
Can you hear the question one more time?
What's a good substitution we can make?
That the R is 9.
How'd you get that?
Since x to the second power plus y to the second power is equals to R2. So I would say that is 3 to the second power, so that's why they got 9.
Okay.
So R is equals to 3.
So everywhere you see the x squared plus y squared, you can replace it with an r squared, exactly. So I'm gonna take this side, I'm gonna replace it with r squared equals 9, yeah? And then we can take the square root and we'll end up with r equals 3, okay? Now, this is a polar equation that represents the same graph as x squared plus y squared equals 9. All right. Now, x squared plus y squared equals 9 is a circle, and it has a radius of 3. And so this r equals 3 is a way of representing a circle in polar form, okay? So it's a much simpler equation, and sometimes it's a lot easier to work with, especially when you get to Calc 2 and Calc 3. So that's why we're kind of practicing how to switch back and forth, okay? All right, so let's try and do some substitutions for example number 6. Should we try the same strategy, replace x squared plus y squared with r squared?
Should I divide the y for both sides?
I wouldn't. But I agree we need to do something with that y, right?
Yeah.
So
Could it be r squared times y?
well, what does the x squared plus y squared substitute into?
R squared.
R squared, right? But we can't get rid of that equal sign. Like the equal sign's still there. We have to keep it. But what can we sub in for y?
Square root of y to the second.
R sinus theta?
Yeah, look at all the equations that you have. Pick the easiest one. We had one that already is solved for y. So everywhere I see a y, I can put r sine theta, okay? So we got to be ready to look at all the different options, not just say we used one and let's keep using the same one. We got to build that flexibility in our brains to say, I tried this one, let me see what else might work for something else, okay? Now, here's the deal. I got a quadratic because I have an r squared. Anytime I see a quadratic, I want to move everything to one side, set it equal to 0. And then I want to factor. So r minus 6 sine theta equals 0. Okay? This allows me to set up two mini equations. So I've got r equals 0 and r minus 6 theta equals 0. This I can solve to say r equals 6 sine theta. And so if you remember in our exponentials and logs unit, some of our answers were extraneous answers. So this r equals 0 is just a point. So we don't count that as an equation because it just represents a point at the origin. But this r equals 6 sine theta is an equation that represents x squared plus y squared equals 6y. Okay, so this and this, if I graph them, will give me the same shape. All right, now sometimes we have to go backwards, right? We know how to convert to polar now, or we know how to convert to rectangular, and now we want to convert back to polar, all right? So if I take a look at y equals 3x plus 2, let's see. Which of my equations might be good to substitute in for y equals 3x plus 2?
Would it be the r squared equals x squared plus y squared?
Well, I don't have a y squared, right? I just have a y.
Then could it be the tangent?
That is a y. I mean, I could do that, but I can't just plug in tangent theta because that's what y over x equals.
Should we substitute the y for r sine and the x for r cosine?
Yeah, we could definitely give that a go. So we've got these other equations here, right? We got to look at the full list of equations, see what matches most easily. And if you already have something solved for x and y, why not just use those? Okay. So for y, I'm going to put r sine theta equals 3r cosine theta plus 2. And so now what I'm going to do is I want to go ahead and move all of my r's to one side. And then I'm going to factor out that r. What's my last step here to get r by itself?
Divide the expression.
Divide that expression, good. So believe it or not, this equation in polar form represents a line. If I graph this and I graph y equals 3x plus 2, I get the same graph. And in this case, I would argue that the rectangular form, the y equals 3x plus 2, is way easier than the polar form, okay? So sometimes the polar is easier, sometimes the rectangular is easier. We'll really just need to look at it case by case, all right? All right, we got one last equation to take a look at. So we have a polar equation, and I'd like us to find the rectangular equation, okay? So take a moment to try some first steps, and then let's share some ideas, see what we have. All right, so what are some ideas that folks have out there?
The first step would be multiplying r times 1 minus 2 cos theta.
Okay, so r times 1 minus 2 cosine theta equals 3. Okay, I like that. I think sometimes getting rid of fractions makes our brains a little happier. What do we want to do from here?
Would distributing it work?
What do other folks think? Anybody think distribution?
Should we replace that cosine to x?
X equals r cosine theta,
Okay.
not just cosine theta.
Will we divide
Divide by what?
by r?
Why would you want to divide by r? Like, what are you hoping that will get you?
Hmm. Well, I was thinking about dividing by the expression, but I'm not sure how the r equaling 3 divided by the expression would fit into any of the formulas we have.
Okay.
But I know I wanted to divide.
Okay. Well, one of the things that we really got to think about is not just like, let's just pick something, but try and think about getting closer to one of the equations we have here. So, what are our thoughts on distribution? Does that get us closer to anything that we have up there or not?
Yes, because then we can convert it to x and y terms.
Ah, okay. So sometimes when we're thinking about what steps to do next, it's actually worse if we only start with just like, let's just try something. But the more we can encourage ourselves to think like, if I try this, what else will happen? Then I think that's what really gets us to be successful at this higher level math. Because I can't give you like step by step, like every time you see this problem, here's what you do. And so we really need to have these conversations like, all right, how do we get closer to it? Right. So let's try that distribution, because the goal is not just to do something, but to try and match the equations we have above. So if we distribute, we get r minus 2r cosine theta equals 3. And what was that you said? What can we substitute now?
For x, r cosine of theta.
Okay, so r cosine theta is going to become x. Because we said from above that r cosine theta equals x. Okay, so now we're starting to make progress, right? We've gotten rid of the theta, and now we have an x. So if we think about this strategically, the next thing we have to do is we got to get rid of that r, right? What can we do to get rid of that r?
Do you mean by isolate the r?
No, I can't have a rectangular equation with r's. I only can have x's and y's.
Multiply by its reciprocal.
If I multiply by its reciprocal, I'm going to get r's in other places. I mean, if I do that, I'll get 1 minus 2x over r equals 3 over r. So I still have an r.
Would you plug in x plus y for r?
Tell me why you're saying plug in x plus y.
Because x squared plus y squared equals r squared, and it's just one r, so you would just do x plus y instead.
All right, so this equation, right, that was familiar to everyone from above. So your reasoning was you only want r, not the square root. So how do you get rid, or not the square, so how do you get rid of that square?
You square root it.
You square root it. This, folks, does not simplify to this, okay? Probably one of the top 10 mistakes. That x squared plus y squared does not reduce to x plus y. However, I love what you were thinking in that you had an r squared, so if you had the r, you could just plug that in. That part of the thinking is great, okay? So let's go back to this one. Everywhere I see an r, I'm going to put the square root of x squared plus y squared. And then now I have the rest of it. Do I have any r's or thetas left in this equation? I don't see any. So that means that I've got my equation now in rectangular form. So this is in rectangular form. Okay. Now, for those of us who are planning to go on to calculus, which I hope you are, because I think this is a terrible class to take if you don't have to go on to calculus. But if you're planning on going to calculus, this kind of thinking is definitely really important, okay? So that's why I'm trying to spend time to get you guys to share your ideas, because whether you're right or whether you're wrong is not really the point. The point is to figure out how mathematicians think so that later on when you're approaching these problems, you're not like, oh, I can't do it unless somebody tells me the exact steps, that you're starting to step outside of that and be like, well, here are a few ideas I could try, and if I try this, okay, maybe I tried dividing by the reciprocal, and in this case it didn't really work, so I'm willing to go back to my original and kind of try something else. Okay, that's the kind of thinking that I'm trying to get us to develop here. Okay, it's not comfortable, it's not easy, and it sucks to say answers that are not correct, especially on a video, but I appreciate that thinking, because without it, how are we ever going to know how other people think? Okay, so that's all the converting business. Okay, we've got one last case of converting, and then I'm not sure we'll get to the graphs, but I can always send you a link to my videos for the graphs. So for example 9 here, it says find the rectangular equation for r equals 2 sine theta, or sine 2 theta, okay? So of all the things that we have learned recently, this is the other part about pre-calc. Everything that you learn builds upon it, and then when you get to calculus, you're expected to remember all of this so you can use it in a more complicated problem. Okay, so if it feels different from previous math classes where you like learn something and then you forget about it, it is definitely different in that way. All right, but think back to all the things that we have learned and what things start to jump out at folks.
Should I replace that sign, the double angle identity for that?
I love it. Double angle. Just because it was the last chapter doesn't mean it's not important anymore, right? So sometimes we see, when we see the 2 theta, that's a really good place to start thinking, oh, maybe I need a double angle identity, okay? So let's try it. Let's see. We get r equals, and what is the double angle identity for sine 2 theta?
2 times sine times cosine.
Good. 2 sine theta cosine theta. Okay. All right. So I've got r's and thetas, but they look a little different now. It's not 2 theta anymore. It's just a regular theta. Okay. So let's see what we can do to substitute. What are some ideas?
Should we put everything to the second power?
Okay, that would give you r squared equals 4 sine squared cosine squared.
Well, since it's a rectangular equation, do we need to get the r into x and y?
Yeah, we need to get r's into x's and y's. We need thetas to go away also. Are there parts of this that we can match with any of those equations we saw before?
You can just transfer the r to the square root of x squared plus y squared. But I wouldn't know how to get rid of the theta.
Okay, so that's a good start, right? We're like, maybe we could do that. We could at least get one side taken care of.
Could we change those? Never mind.
Can we match sine theta with any part of another question or equation? Or rather, what equation has sine theta in it and what can we do with it?
Y equals R sine theta, but wouldn't the sine theta need an R transferred to Y?
Okay. How do you match just the sine theta part? Like sine theta equals what?
Y divided by R.
Yeah, y divided by r. So what that means is everywhere I see sine theta, I can replace it with y divided by r. Okay, so I have 2 times y divided by r. Okay, times, let's use some similar reasoning to try and get rid of the cosine. What can we write instead of cosine?
X over R.
X over r. Okay. All right. So I've got square root of x squared plus y squared equals 2xy over r squared. Well, we got rid of quite a bit, right? We started by taking a chance to say, I could get rid of one side. I don't know what to do with the other yet, but let me at least write that down. And then the other side, we were like, okay, well, maybe we take some equations that we have and solve for the part that we want and then make that substitution, right? And I think we're in the home stretch here. What do we do now?
Change that to R squared.
All right, what are we changing it to?
X squared plus Y squared.
All righty. All right. That's kind of a gross looking equation, but it's the equation. Okay, so again, this goes back to the point that sometimes x's and y's are not necessarily easier. Look at how smooth the polar form was. R equals sine 2 theta, done. But the rectangular form had a lot more parts to it, okay? And so in this case, like when we see curves like sine 2 theta, we really want to be thinking, okay, those are defined more easily by polar. So knowing what they look like is a lot more helpful, so that we can generate graphs and we can do a lot of things with those graphs once we get to calculus, okay? So thanks for sticking that through. I know that that's not super easy to do, but you know, part of that development is trying to be uncomfortable, but also hopefully feeling supported in that discomfort, okay? So we are about out of time. So what I think I'm gonna do is this. I'll send you the link to the videos that I have for the graphs of these. But if you're someone who is a very visual learner, you might wanna try Desmos, okay? So Desmos is a free app that you can get for your phone, for your tablet. You can just go to Desmos and the website and it will pull up a graphing calculator, okay? And play around with the different graphs that we have here. So let me show you Desmos in case you don't know what it is yet, right? Look something like this, free graphing, okay? But you see how this is like XY coordinates, right? So if you click on the little wrench up here in the top right-hand corner, and you go to the part where it says grid, if you have the one with the XY, it will give you XY, but if you have the one with polar, the one with the circles, now you've got polar graph, okay? So let's take a look at what that graph looks like of r sine 2 theta. So r equals sine of 2, where's my theta? Theta. Okay. And so r equals sine 2 theta, or that very complicated graph that we just looked at, is really no more than something we call a rose curve. Okay, so there's a certain number of petals. Each petal can be graphed using a regular XY table. Okay. But if you go through all the options I have in the rest of the notes, you can kind of play around with Desmos, plug in different numbers and see what happens to the different graphs, okay? And again, I'll send out links to videos for that so you can kind of play around with that. But knowing what these graphs look like is definitely super, super helpful for not Calc 1, but actually for Calc 2, okay? So I know that's kind of a few semesters away, but I just wanted to put that in there for you so you kind of know where you're headed and not just like, why am I doing this, but when am I going to use it again, okay? So on that note, I'm going to stop the share here. And I know that you folks turned in exams to me yesterday, so I should have those graded by the end of the weekend, all right? So double check your Canvas for grades and let me know if you have any questions. But I would encourage you to take a look at what assignments you're missing, because we're about 3 weeks from the end, which means there's not a whole lot of time to make up points, all right? So whatever you need to do, please make sure that you are on top of that. I do go in pretty quickly after assignments are due and put a 0 in there so you know if you're missing something, okay? But I like to keep that grade book current just so you know where you stand, and it's a reminder. I think a 0 is a very powerful reminder of like, oh shoot, I need to go back and do that, rather than like the night before the semester ends and you're like, I forgot about all these assignments. Okay, so go back in, see what you need to do if that applies to you, and make sure you're reading all those emails so you know when tests and other assignments are due. Okay.
Thank you.
All right, folks, have a good rest of your weekend. Be well.
Thank you.
Was there